We are Team 6 and we are here to present our IoT project. Do you know that 14% of the food produced is lost before reaching the consumers and 17% is wasted, leading to 526 million tons of food waste annually due to inadequate temperature monitoring in the cold supply chain? As such, our group aims to employ a solution where we use advanced mesh technologies utilizing LoRa and Wi-Fi to ensure robust and efficient temperature monitoring across the supply chain, aiming to minimize food spoilage and waste. The key components used are LoRa mesh for its extensive coverage, ensures reliable data collection and transfer, Wi-Fi to facilitate data uploading to the cloud, Wi-Fi mesh for its robust real-time network connectivity, and Airtable database for data management and analysis.
Our demo concept proposes a solution to enable temperature sensor data collection throughout the supply chain to monitor cooler and freezer temperature levels. This solution empowers manufacturers to assess and regulate product storage conditions, as well as address inadequate cooling or low coolant gas level throughout their supply chain. This continuous monitoring capability enhances quality assurance, reduces spoilage, and fosters improved communication between their distribution network. Our demo proposed using mesh networks to enable mostly offline data capturing. This method of data collection is cost efficient, as there is no need to spend extra cost on internet access using an LTE-enabled SIM card. Furthermore, mesh networks are reliable and serve as a backup to store data when other mesh nodes fail, which we will see later on in the demo. As our as another backup method, we store all readings inside an SD card. Lastly, our solution is also hands-free, meaning there is no need for any personnel to press any button to send or collect data, which means that the data collection process is seamless.
Hardwares used include 3 LilyGo boards, which serve as a bridge in the LoRa mesh within the factory environment. It can switch between Wi-Fi and LoRa connectivity to maintain constant data flow even when in transit. It also transfers sensor data to each other within distributor freezers to ensure no blind spots in temperature monitoring. An SD card for demo purposes provides data backup in the event of hardware failures. Sensor data is also saved into the SD card at fixed intervals. Phone hotspot is used to provide internet connectivity to devices in the factory compound. The temperature sensors integrated into the ESP32 chips on the LilyGo boards are used for real-time temperature monitoring of goods in the supply chain. Softwares used include the LoRa mesh for data transfer from trucks and driver nodes to the LoRa bridge. It ensures data can be relayed over long distances reliably and also acts as a backup data collection for other nodes at the factory compound. Wi-Fi mesh provides real-time offline connectivity in places where the device is placed. It shares sensor data between devices within proximity and also serves as a backup data collection for nodes at the customer compound. Point-to-point Wi-Fi is used for the uploading of data from the LoRa bridge node to the API server. The Netlify function's API server processes data from devices sent via the LoRa bridge. It also has a HTTP webhook that devices can call to upload their data. Finally, the Airtable database stores sensor data to create a historical record of data throughout the supply chain. It also allows users to sort, filter, and visualize data to identify any trends, and also provides access to data for other applications, for instance, email or notifications.
For our demo, we will be presenting in a storytelling way such that it is simpler to understand. Our solution will mostly focus on business to business, so we'll be presenting it as such, where the driver will leave from the factory to the customer's place. So one node will be inside the customer's chiller, and another node will be, we will assume that the driver will be holding on to, and another node will be inside the truck. For stage 1 of our demo, the driver will be driving to the customer's place. So we will turn off the customer's chiller node for now and turn on the driver and truck node. As we can see on the display, the temperatures of both nodes is shared using a Wi-Fi mesh. For stage 2 of our demo, the driver will be bringing his node to the customer's place. So we will turn off the truck node which is inside the truck, simulating that the driver is delivering the item to the customer. As we can see on the display, when the driver node is approaching the customer's chiller node, information will be shared to the other nodes even though the node is offline. The driver node will then capture the temperature within the customer's chiller. As we can see, there are 3 rows of data in the driver and the customer's node. For stage 3, we will turn off the customer's chiller node and simulate going back to the truck. So the wireless mesh is now syncing. As we can see on the display, all the nodes temperatures has been collected and displayed. For stage 4, we will simulate the driver and truck nodes going back to the factory. At the factory, the nodes will be connected through a LoRa mesh, and the bridge node will be connected to a Wi-Fi hotspot on my phone. So the driver and the truck nodes will then upload the data to the bridge node and then to be uploaded to an API endpoint to be displayed on the dashboard. So after uploading, the data will be then cleared on the node's device. So I'll plug on the factory node now. As we can see, there are still 3 rows of data on both the truck and driver nodes from the previous stage. So the data are both synced to the factory node. And if we can see on the display here, the updated temperatures are at 2:33 p.m. So for the last stage of the demo, we'll be showing the uploading of data from the bridge node to the Airtable database, as well as visualization. As seen in the Airtable database, the rows are indeed highlighted every 5 seconds for demonstration purposes to show that it is indeed updating from the bridge node. After the data is updated in Airtable, our user interface dashboard will obtain the data from Airtable. So temperatures above 25 degrees will be highlighted in red, while those below will be in green. Lastly, we'll be showing how our data is backed up to an SD card. For demonstration purposes, only one SD card is used for the bridge node. So data received from the bridge node is stored in fixed intervals as a JSON structure inside the SD card, which is inside the sensors.log file. So data which is stored inside the log file can then be retrieved in the event of a device failure.
In conclusion, our solution is cost-effective because mesh network solution is entirely offline except when we are in the factory compound. Next, reliability. Through the use of mesh and SD card, we prevent single point of failure to ensure that temperature data is reliable at all times. Next, low maintenance. Our solution is hands-free as it only requires the monitoring of dashboard for temperature anomalies. So some of the use cases for our project include smart agriculture, where we can extend our solution to monitor temperature in greenhouses, soil temperature and ambient temperatures in outdoor fields. Next, building management. Deploy system for monitoring indoor temperature in commercial building, warehouses and data centers. Lastly, healthcare. Utilize temperature monitoring for monitoring temperature sensitive equipment and medication storage in hospitals and pharmacies. With this, I end our presentation. Thank you.